Okay, this is chi-squared fit, goodness of fit scenario 2, and this is page 217 of the note spiral, and I believe this is a homework problem. So a grocery store manager wishes to determine whether a certain product will sell equally well in any of the 5 locations in the store. 5 displays are set up, 1 in each location, and the resulting numbers of the products are sold are noted. Is there evidence that location makes a difference? Test at the 10% level. And this is probably a key word. And so my null hypothesis in this situation, by the way, because it says, because this says difference, I'm like, okay, that's a key word. And then I look and go multiple categories. This is going to be a chi-squared test. All right. So this is a chi-squared test. I only have 1 variable, multiple categories, chi-squared goodness of fit. So I'm going to go ahead as always and sum this up, and I find that my total right here, when I add all these up, adds up to 206. Please notice these are all whole numbers, so the counted data thing condition is met. And we have a couple ways to go. They're saying they're equal, sell equally. So in other words, if they're equal, we're talking about a uniform distribution. So we can say the product sales follows a uniform distribution. Now, if that bothers you, and it's okay if it does, or if you don't recognize that, you can say sales are the same for each location. That's the null. The sales are the same for each location. The alternative is the sales, the product sales do not follow a uniform or are different. Okay. So you can sit there and say that the sales do not follow a uniform distribution or the sales are different for each location. Please remember, when we're doing a chi-squared goodness of fit, the first one is always going to be based on equal. So in other words, it equals a uniform. It is a uniform distribution. All right. All right, our conditions. This doesn't say that it's a random sample. So since it doesn't say, we're gonna have to go random sample, not given. But we assume it's representative of the sales data. And we must assume that the sample is representative of the sales data. Two, that's our expected values. Well, we don't know them yet, so we're gonna have to calculate them. Well, they're expecting them to be the same for each place. So I should be able to take 206 and I divide by 5. And when I do that, so I added all these up, got to 206. I divide by the 5 categories. 206 divided by 5 ends up being 41.2. So each of these, I'm expecting 41.2. And you're like, hey, Mr. Spencer, but that's not a whole number, that's a decimal. That's right. The observed can have to be a whole number. So the observed values must be a whole, the OBS, but the expected values, they don't have to be, but the expected have to be greater than 5 and the observed don't. All right, so this sums to 206. All right, all expected values are greater than 5. See the table. All right. And you do have to show them. The next thing, all observed values are counted data, whole numbers. Slash whole numbers. Our formula, chi-squared equals observed minus expected squared over expected. And our degrees of freedom, that's our number of categories. And we have 1, 2, 3, 4, 5 categories, 5 locations. So 5 minus 1 is 4. So our degrees of freedom is cat minus 1, which is 5 minus 4. 5 minus 1 is 4. Showing our work for our formula, all we have to do is show the first and last. So we observed a 43. So this is 43 minus 41.2 over 41.2. Don't forget to square this. Plus dot 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 plus 48 minus 41.2 over 41.2. So stat edit, I've entered my observed values right here, 43, 29, 52, 34, and 48. Now I need to enter my expected, which is 41.2. Second quit, stat, test, chi-squared goodness of fit. L1, L2 degrees of freedom is 4. And we end up getting a chi-squared equal to 8.903 with a p-value of 0.063. We set our alpha. We said our alpha was going to be 0.01. Excuse me, not 0.01, 0.1. I'm wrong, 0.1. And 100 is definitely greater. So this is our p-value is less. So we reject the null. And while we have it up here, we're going to look at our contributions real quickly. So we have this, the first one, 0.07. The next one is 3.6, 2.8, 1.2, and 1.1. So if I'm scrolling back, 3.6, which was the second one, 3.6 was the largest. So that one has the greatest contribution. So basically location 2 has the largest value. All right. I'm going to go ahead and write those values down. So we have a CNT RB of 0.0786, 3.612. I have this next one written down wrong. Yep. 2.831. 2.831. 1.258. And the last one is 1.122. And if I sum these together, they should equal that within rounding. Okay. And this is location, this is location 1, location 2, location 3, location 4, location 5. Location 2 is the biggest value, so it has the greatest impact. So location 2 has the greatest impact. So our conclusion. Our P value is 0.063. We reject the null. There is sufficient. There's enough evidence. In other words, there is sufficient evidence at alpha equal 0.10, not a 0.05, but a 0.10, to suggest that the distribution of sales is not uniform. Simplified language says, simplified language would say product location impacts sales. Okay, product location impacts sales. We have evidence to say that. Or product placement impacts sales. And we know that location 2 had the biggest impact. All right, ended up being a negative impact, but product location number 2 apparently is a bad location. You're like, how did you know it was a negative? That's a great question. I know it was negative because it was below. So this had the greatest negative impact, and this one would have had the greatest positive impact. It was farther above, this was farther below. And it was easy to tell because they were all the same, because the expected values were all the same. All right, so I'll slide this back up so you can finish copying it down. And that will conclude this video. Thank you.